3.7 Bonding and Physical Properties. One of the key ideas of science is that matter, which is anything with mass, is made of tiny particles. It is particulate. These particles are in motion, which means they have kinetic energy. To understand the differences between the three states of matter, gas, liquid, and solid, you need to be able to explain the energy changes associated with changes between these physical states. First of all, heating a solid. When you first heat a solid and supply energy to the particles, it makes them vibrate more about a fixed position. This slightly increases the average distances between particles, and so the solid expands. Turning a solid into liquid, melting, also called fusion. In order to turn a solid with its ordered, closely packed, vibrating particles into a liquid, where the particles are moving randomly but still closely together, you have to supply more energy. This energy is needed to weaken the forces that act between the particles, holding them together in the solid state. The energy needed is called the latent heat of melting, or more correctly, the enthalpy change of melting. While a solid is melting, the temperature does not change because the heat energy provided is absorbed as the forces between particles are weakened. Now, enthalpy is the energy change measured under constant pressure, whilst temperature depends on the average kinetic energy of the particles and is therefore related to their speed. The greater the energy, the faster they go. When you heat a liquid, you supply energy to the particles, which makes them move more quickly. They have more kinetic energy. On average, the particles move a little further apart, so liquids also expand on heating. Turning a liquid to gas, boiling, also called vaporization. In order to turn a liquid into a gas, you need to supply enough energy to break all the intermolecular forces between the particles. A gas consists of particles that are far apart and moving independently. The energy needed is called the latent heat of vaporization, or more correctly, the enthalpy change of vaporization. As with melting, there is no temperature change during the process of boiling. As you heat a gas, the particles gain kinetic energy and move faster. They get much further apart, and so gases expand a great deal on heating. Crystals. Crystals are solids. The particles have a regular arrangement and are held together by forces of attraction. These could be strong bonds, covalent, ionic or metallic, or weaker intermolecular forces, van der Waals, dipole-dipole, or hydrogen bonds. The strength of the forces of attraction between the particles in the crystal affects the physical properties of that crystal. For example, the stronger the force, the higher the melting temperature, and the greater the enthalpy of fusion, the more difficult they are to melt. There are 4 basic crystal types: ionic, metallic, and macromolecular. Ionic compounds have strong electrostatic attraction between oppositely charged ions. Sodium chloride, NaCl, is a typical ionic crystal. See topic 3.1. Ionic compounds have high melting points. This is a result of the strong electrostatic attraction which extends throughout the structure. These require a lot of energy to break in order for the ions to move apart from each other. For example, the melting point of sodium chloride is 801 degrees Celsius or 1074 degrees Kelvin. Metals exist as a lattice of positive ions embedded in a delocalized sea of electrons. See topic 3.3. Again, the attraction of positive to negative extends throughout the crystal. The high melting temperature is a result of these strong metallic bonds. Molecular crystals consist of molecules held in regular array by intermolecular forces. Covalent bonds within the molecules hold the atoms together, but they do not act between the molecules. Intermolecular forces are much weaker than covalent, ionic, or metallic bonds. So molecular crystals have low melting temperatures and low enthalpies of melting. Iodine is an example of a molecular crystal. A strong covalent bond holds pairs of iodine atoms together to form I2 molecules. Since iodide molecules have a large number of electrons, the van der Waals forces are strong enough to hold the molecules together as a solid. But van der Waals forces are much weaker than covalent bonds, giving iodide the following properties. Crystals are soft and break easily. Low melting temperature, about 114 degrees Celsius and or 387 Kelvin, and sublimes readily to form gaseous iodine molecules. And it does not conduct electricity because there are no charged particles to carry the charge. Covalent compounds are not always made up of small molecules though. In some substances, the covalent bonds extend throughout the compound and have the typical property of a giant structure held together with strong bonds. Therefore, a high melting temperature is present. There are many examples of macromolecular crystals, including diamond and graphite. Diamond and graphite are both made of the element carbon only. They are called polymorphs or allotropes of carbon. They are very different materials because their atoms are differently bonded and arranged. They are examples of macromolecular structures. Diamond consists of pure carbon with covalent bonding between every carbon atom. The bonds spread throughout the structure, which is why it is a giant structure. A carbon atom has 4 electrons in its outer shell. In a diamond, each carbon atom forms 4 single covalent bonds with other carbon atoms. These 4 electron pairs repel each other, following the rules of the electron pair repulsion theory. In 3 dimensions, the bonds actually point to the corners of a tetrahedron with bond angles of 109.5 degrees. Each carbon atom is in an identical position to the structure, surrounded by 4 other carbon atoms. The atoms form a giant 3-dimensional lattice of strong covalent bonds, which is why diamond has the following properties. It is very hard, one of the hardest materials known. It has a very high melting temperature, over 3,700 Kelvin. But Again, it actually does not conduct electricity because there are no free charge particles to carry the charge. Graphite also consists of pure carbon, but the atoms are bonded and arranged differently from the diamond. Graphite has two sorts of bonding, strong covalent and the weaker van der Waals forces. In graphite, each carbon atom forms 3 single covalent bonds to other carbon atoms. As predicted by bonding electron pair repulsion theory, these form a flat trigonal arrangement, sometimes called trigonal planar, with a bond angle of 120 degrees. This leaves each carbon atom with a spare electron in a p orbital that is not part of the 3 single covalent bonds. This arrangement produces a 2-dimensional layer of linked hexagons of carbon atoms, rather like a chicken wire fence. The p orbitals with a spare electron merge above and below the plane of the carbon atoms in each layer. These electrons can move anywhere within the layer. They are delocalized. This adds to the strength of the bonding, and it's rather like the delocalized sea of electrons in a metal, but in 2 dimensions only. These delocalized electrons are what makes graphite conduct electricity, a very rare thing for a non-metal. They can travel freely through the material, though graphite will only conduct along the hexagonal planes, not at right angles to them. There is no covalent bonding between the layers of carbon atoms. They are held together by the much weaker van der Waals forces. This weak intermolecular force of attraction means that the layers can slide across one another, making graphite soft and flaky. It is the lead in pencils. The flakiness allows the graphite layers to transfer from the pencil to the paper. So, graphite is a soft material, but it has a very high melting temperature, and in fact it breaks down before it melts. This is because of the strong network of covalent bonds, which make it a giant structure. It conducts electricity along the planes of the hexagons. Most recently, a number of other forms of pure carbon have been discovered. Chemists found the first one was they were looking for molecules in outer space. The structures of these new forms of carbon include closed cages of carbon atoms and also tubes called nanotubes. The most famous is Buckminster Fullerene, C60, in which atoms are arranged into a football-like shape. Harry Kroto and colleagues received the Nobel Prize for the discovery. Now, scientists are investigating many uses for the new materials. So to summarize, there are 3 types of strong bonding that hold atoms together: ionic, covalent, and metallic. All 3 involve the outer electrons of the atoms concerned. In covalent bonding, the electrons are shared between atoms. In ionic bonding, electrons are transferred from metal atoms to non-metal atoms. In metallic bonding, electrons are spread between metal atoms to form a lattice of ions held together by delocalized electrons. If you know what the compound is, you can usually tell the type of bonding from the types of atoms that it contains. Metal atoms only do metallic bonding. Metal and non-metal do ionic. And non-metal atoms only do covalent. The 3 types of bonding give rise to different properties, such as electrical conductivity. Now, the property that best tells us what sort of bonding you have is the before mentioned electrical conductivity. Metals and alloys an alloy is a mixture of metals, conduct electricity well in both the solid and liquid state due to their metallic bonding. The current is carried by the delocalized electrons that hold the metal ion together. Ionic compounds only conduct electricity in the liquid state, or when dissolved in water. They do not conduct when they are solid. The current is carried by the movement of ions towards the electrode of opposite charge. The ions are free to move when the ionic compound is liquid or dissolved in water. In the solid state, they are fixed rigidly in a position in the ionic lattice. Generally, covalently bonded substances do not conduct electricity in either the solid or liquid state. This is because there are no charged particles to carry the current. Covalent compounds are often insoluble in water, but some react to form ions. For example, ethanoic acid, present in vinegar. The solutions can then conduct electricity. You can therefore decide what type of bonding a substance has by looking at how it conducts electricity. This is summarized below. So, metallic bonding will conduct electricity in its solid form, in its liquid form, and in aqueous solution. Ionic will conduct electricity not in its solid, but in its liquid form and in aqueous solution. Covalent won't conduct electricity in any of those options. Structure describes the arrangement in which atoms, ions, or molecules are held together in space. There are four main types: simple molecular, macromolecular, joint covalent, giant ionic, and metallic. A simple molecular structure is composed of small molecules, small groups of atoms strongly held together by covalent bonding. The forces of attraction between molecules are much weaker, often over 50 times weaker than a covalent bond, and are called intermolecular forces. Examples of molecules include Cl2, H2O, H2SO4, and NH3. A macromolecular structure is one in which large numbers of atoms are linked in a regular three-dimensional arrangement by covalent bonds. Examples include diamond and silicon dioxide, silica, the main constituent of sand. A giant ionic structure consists of a lattice of positive ions, each surrounded in a regular arrangement by negative ions and vice versa. A metallic structure consists of a regular lattice of positively charged metal ions held together by clouds of delocalized electrons. Macromolecular, giant ionic, and metallic structures are often called giant structures because they have a regular three-dimensional arrangement of atoms in contrast to simple molecular structures. The property that best tells us if a structure is giant or simple molecular is the melting or boiling point. Simple molecular compounds have low melting and boiling points. Giant structures generally have high melting and boiling points. If a compound has a low melting and boiling point, it has a simple molecular structure. All molecular compounds are covalently bonded. So all compounds with low melting and boiling points must have covalent bonding. However, a compound with covalent bonding may have either a giant structure or a simple molecular structure, and therefore may have either a high or low melting and boiling point. When you melt and boil simple molecular compounds, you're breaking the intermolecular forces between the molecules, not the covalent bonds within them. So the strength of the intermolecular forces determines the melting and boiling point. There are three types of intermolecular forces. In order of increasing strength, these are van der Waals, which act between all molecules, dipole-dipole, which act between molecules with permanent dipoles, hydrogen bonds, which act between the molecules formed when highly electronegative atoms, oxygen, nitrogen, and fluorine, and hydrogen atoms are covalently bonded.